Okay, hello everyone. Welcome to my talk. My name is Thomas from SAP, now in SAP Linux Web. Before I was in HANA development, and I prepared this presentation and wrote the paper together with my colleague Enno Volkert from HANA development. And yeah, I'm going to present what we have done in performance analysis of containerized database management systems. So in my talk, I will mainly focus on the operating system things and their impact on the database. So I will present what OS containers are and how different containers can be configured. That, of course, affect the resources that a container has, and I will talk about the operations on the resources, and finally present the evaluation of different configurations. And especially we are presenting a kind of performance analysis methodology to easily compare different configurations. So maybe some of you guys have heard about OS containers already, but basically my talk, my take is that they are essentially virtualization, but on a higher level than we have with the previous, or with the conventional hardware virtualization. So you see that on top of the hardware, nowadays we have a hypervisor with the CPU API as the interface. The hypervisor now presents the vCPU API towards everything that's running on top. And that's traditionally the VM. And nowadays, for the containerized cloud systems, in the VM we have a container host OS, and the container host OS has the kernel API as the interface, and on top of that one is running the container itself. And yeah, the container is deployed as an image, similar to a virtual machine image, but again in a slightly different format. That means it includes all the user land for the operating system. So everything that's not the kernel is essentially virtualized and replaced and put into the container. Only the top layer of the container is mutable, but the mutations are volatile, so they are not persistent. For the database, it means that the persistency needs to be stored somewhere else, like outside of the container, in some kind of network volume, or can be local volume. Anyways, outside of the container and somehow mapped into the container. Yeah, so basically the virtualization done by the OS container is not very dependent on the hardware below, but what's important now is the kernel API and the resources that are given to the container in terms of CPU threads or cores, and the memory that is available, and some other things. These resources can either be partitioned from the container host system to the containers running on top, or they can be virtualized in the manner that some kind of virtual resource is created that somehow builds on some other physical resources. And because the virtualization layer is higher for the container compared to the hardware-based virtualization, the isolation of the containers is more difficult to achieve. So that means we have to take special care that the containers are isolated well in terms of functionality, of course, so that one container cannot look into the other container, and also performance-wise. And what's popular nowadays is the container orchestration, so not just running the container themselves, but somehow building a whole system based on containers, like all the big cloud IaaS providers are doing that with the Kubernetes deployments. For us, that means that somehow cross-operating system compatibility needs to be considered. That means that the host OS can have a different operating system than the guest OS. But that's just as a side note, because that's something with supportability, but not so relevant now. So basically what we are facing, we think of different container configurations and how they can be compared against each other. So what we contribute in our paper is basically this testing methodology to compare different container configurations with a wide range of workload. So not just focusing on one specific workload or a few workloads, but trying to be as general as possible to give a wide insight. And we exemplify this with the Docker container engine and of course the SAP HANA database, which is our own one. So coming to the container resources, and that's basically straightforward. The CPU is one of the most important resources. Actually, Docker gives two ways to configure the CPU. Either you can just specify the total number of CPUs that should be available to a container. That's just called CPUs configuration. Or you can specify nowadays exactly the list of hardware threads that are available to a container. That's CPU sets. So you basically give a list of the hardware threads that the container is allowed to use. And then the container engine or the operating system take care of scheduling the container on those CPUs that are available. All these resources are nowadays possible to change dynamically during the runtime of a container. So yeah, the database also takes care of that. Volunteer memory is the another kind of resource. For the database, obviously we don't want to over-provision to avoid out-of-memory situations. But what we want to do is we want to make the memory available to a container somehow aware of NUMA topology, so that the container can actually benefit from topology, as opposed to being spread all over different NUMA nodes and having much inter-node communication. About the persistency, I already said the persistency is mapped from somewhere outside of the container. It doesn't make much sense to store it in the container, which is volatile. And the network is another resource. We can look into that in detail, just because we don't think that the network would be the bottleneck or have high relevance under the containerization. So now let's have a look at operations. First of all, for managing the log volume of the database, you see we have 3 containers in this example, CA, CD, CC. And the two options are either to share the storage volumes, share them among all the containers on the container host system, which of course, if we do striping of the volumes, increases the performance, throughput, and also latency. And as we share the volumes among all the containers, it can help to reduce the fragmentation and use the storage efficiently. On the other hand, the alternative is to have dedicated volumes for the containers. So now you can see that we have again the containers CA, CD, CC, and each one is provided with their own storage volumes. So that means the data is physically separated, Of course, depending on the configuration, but anyways, the performance might be lower just because we have fewer stripes available to each container, and the storage consumption is generally increased as compared to the shared volumes. Similar thing about the CPUs. I already mentioned before about the configuration CPUs, which just specifies the number of CPUs, and the container engine can choose which CPUs the containers run on. So we have, in this example, 4 sockets, S1, S2, S3, S4, and the containers, HPCC, and they just receive a certain number of CPUs or resources, and the system manages it. In this case, maybe it makes sense to over-provision the CPUs, and it's possible very easily. But of course, you lose the control about NUMA placement. Like, you cannot control which socket or which hardware thread the container runs on. The opposite is the alternative is the CPU sets, which allows you to pin the hardware threads to sockets, and that makes it easy to partition, and on the other hand hinders the over-provisioning. But anyways, this is the way how, if you want to go for that, you can achieve NUMA awareness in the sense of NUMA control. And you can see there is some like drawback that you cannot just partition any way you like, or it's harder to reconfigure. More static configuration. And the last thing about the operations I want to talk about is container migrations. Hardware issues and anything make it necessary to migrate a container once in a while. Migration of container means that you cannot just migrate a container. I mean, that's possible somehow in research, but I don't think it's supported anywhere in the commercial container engines. But anyways, you shut down the container, you transfer it to another host, and you start it up again. Actually, with the database, you can have something like a near zero downtime as a system replication, which means you build up a secondary, replicate the database to it, and then switch over to the secondary and migrate that way. But that's more costly because in the end you have to have a secondary available. So you may need to switch the persistency. If you have what we had before, the dedicated volumes here, the dedicated volumes you can just switch around, unmount and remount. With the shared volumes, that's not possible because they are shared, and you cannot just unmount them on some node because the other containers on that node still need the resource. So in that case, you have to copy the persistency. That's kind of the drawback. Now, the performance testing methodology. We have a test suite of about 700 measurement points, OLTP and OLAP queries. So we try to have a little bit of everything inside there, and quite a low coefficient of variation. But there are also some with a higher coefficient of variation, which are essentially still significant for some statements. As I said, we want to compare the containers in different configurations, diverse workload, and isolate or not isolate the containers in the presence of noisy neighbors. So, point is, how do we get an overview of the configurations? We have made some formula, maybe you can look it up in the paper, I'll speed up now a bit. And basically we create bins of regression values and draw histograms, and this allows you to get an insight. So let me explain. The bare metal is just bare metal comparison, and means we have two almost or essentially identical systems, and comparing them should not show a significant difference. And you can see that most is just on the 0, so 0% regression. It gets more interesting in the right case with the virtual machines now. These are still virtual machines, no containers. Without and with noisy neighbors. So this one's without noisy neighbors compared to with noisy neighbors. And you have the 0 here, and you notice that here you see this Q on the right-hand side, which means that with noisy neighbors, you have a certain performance drawback. And this methodology also allows us to state how much impact we have. So the histogram has all the measurement points, and we see that, for example, in this case, the 90% percentile means 90% of the results have less than 3% progression through the noisy neighbors. I hope you got that, because now we have done several comparisons. First of all, with the CPU set, without noisy neighbor compared to with noisy neighbor. And you see here that the CPU set again has a skew on the right. For the noisy neighbors, because the noisy neighbors show some performance regression, or have some performance. Same thing for the CPUs. Actually, a much higher case. You see here, the 0 is almost not achieved. Then we go on. Without noisy neighbors, CPU assignment. Now we compare CPU sets and CPUs against each other. And you see in this case, CPU sets is worse. It has this skew here as opposed to comparing to the 0. And with noisy neighbors, you see that this skew is now on the right side for the CPUs. And what we can conclude from this, these two diagrams is that without noisy neighbors, the CPUs has the advantage, but with noisy neighbors, the CPU set has the advantage. Basically, because the CPU set is partitioning the threads. Okay. The last comparison was about the storage striping options I told you before. And here we see this skew on the left-hand side. That means the dedicated storage has worse performance. And that's caused by, like what I don't have on this slide in detail, are the actual storage comparisons, storage configurations used. So the dedicated storage just uses one stripe per container. And the shared storage has 2 stripes, and we're comparing systems with one noisy neighbor. Okay, that concludes my talk. And I thank you very much for your attention, and I'm ready to receive your questions.
Can you come to the mic? Hi. So it was very interesting. One of the things I wanted to understand was what is frequency that you showed in the last 5-6 graphs. What is the meaning of frequency?
Frequency is essentially just the number of results, or the number of measurement points for that have been observed for this comparison.
Okay, let's say you came up with a metric to actually. I was thinking that these are the number of queries that finished and something like that from that.
Yeah, but actually a number of queries, because we have, from each query we have different measurement points, but essentially we can think of that as different queries giving different results, and then we see if they are better or they are worse on the one or the other side, comparing 2 configurations, and that gives the frequency.
And when you compare the memory use, CPU use, like this.
We could do memory, but in this case we don't. We just use a CPU and elapsed time. Yeah.
Throughput. So one thing pretty interesting is larger customers and production customers is want VMs or full nodes anyway, but from a test point of view and if I see the general pattern, people are moving towards fraction of the core also, or smaller databases. This is made, as you say, the granularity is one core or one thread.
Yeah, okay. I mean, that's the option that the system gives to us. Of course, you can still configure in very fine granular, even using CPU sets, you can specify the same CPU several times.
Okay. Yeah.
Possible it is, but I mean, depends. Actually, absolutely depends on the workload. If you have many systems which just run occasionally, you can go with that.
And that's how I also work, because I think OS doesn't give you more granularity than 0.25, but they, I think, overbook and give, let's say, 10 dBs to one core, but essentially, in worst case, they will fail to actually provide